In this video, we're going to talk about something that I think is really important to understand in trigonometry, and it's something that I think a lot of people don't realize. We're going to talk about approximations of trig function values. So we're at section 2.3. Okay, so what are we talking about here? Approximations of trig function values. Well, to make it clear to you what this is all about, let's first review some of the things we've done so far in section 1.3, 1.4, 2.1, and 2.2. In the first four sections of trigonometry. The first two sections were like a geometry review. So these first four sections here. So at the end of chapter 1, we were introduced to the general definition of trig functions, right? The XY coordinate system, right triangle definition. Okay, but if you think back to the different kinds of example problems that we worked in these two sections, the problems were things like determine the signs of a trig function value, what the sign could be, positive or negative. Or maybe like we were given that the sign of theta is this, and theta is in this quadrant, and so we could use the general definition or Pythagorean identities or any kind of trig identity to find the other trig function values. Or a common type of problem was we were given a point in the Cartesian plane, like an XY point. And the idea was we wanted to think about that point as it makes a line between the origin, which that's the direction of the angle. That represents the direction of the angle. Then with that, find all of the trig function values of that angle. In other problems, instead of a point, we were given the equation of a line, with that line kind of defining the angle direction. But if you think about it, so in either of those cases, in one case, we're actually given a trig function value to start with. And then in the other case, because we have either a point or a line, we can, from that point or that line, we could determine the side lengths of the corresponding triangle, right triangle. And once we have the side lengths, we can go ahead and evaluate the trig function values of that angle. Okay, but that's fine. That gives us good practice of understanding the definition of trig functions, and it gives us like a perspective on calculating them. But, in general, the idea really is, so, okay, if I give you an angle, say theta is equal to 17 degrees, what are all the trig functions of that, right? That's more realistic, isn't it? In reality, you don't have how would you have a point in the plane? I guess you could have a point in the plane if you don't know what angle it corresponds to, but what use is that? Or like if you have the equation of a line that represents a certain angle, okay, but like how would you even get that line in the first place? That equation, unless you just picked a random line that you don't have no idea what the actual angle of that line is. So for trig functions to be useful to us, it really comes down to we need to be able to start with an angle. And that's it. That's all we have. We just have an angle. And then from there, what are the trig functions of that angle? And if you think about it, up to this point in these first four sections, we haven't really ever done that. We've actually only done that for three angles. The three special angles, the 30, 60, and 45 degree angle. But other than that, if you go back to all of these sections and all of the example problems that we worked, it was all about, predict what the sign of the trig function would be. Or, you're given a trig function of theta. You're given one trig function, and with that, then find the other ones. But still, you start with information, trig function information. Or you're given a direction to start with, a point to start with. You're given this information that in reality you wouldn't ever have to start with. Okay, and so again, I'll say it again, for trigonometry to be useful to us, we have to be given any angle, and that's it. That there's no other, the context, that's it. All you have is an angle, and from that, what are the trig functions of that angle? So you can imagine you have this big table of like 1 degree, 2 degrees, 3 degrees, but even more than that, 1 degree, 1.1 degrees, 1.2 degrees. You can input any angle, the decimal of an angle, whatever, and you get the value of the trig function of that angle. So you can think about it, maybe it's not a table that you're going to use, maybe it's a calculator. We'll give you that answer. Now, I mentioned that we actually have been able to calculate trig function values of angles from scratch like this with the special angles, 30, 60, and 45. And with that, we could calculate trig functions not just of those 3 angles, but any angle that has one of those angles as a reference angle. So like 135 degrees, since it has 45 degrees as a reference angle, we can like raw from scratch find the trig function values of 135 degrees. So how did we do this for those angles, those special angles? Well, if you remember we did this in section 2.1, we were just able to use simple concepts from geometry. So any equilateral triangle has the angles are 60 degrees, each angle. Okay, we just arbitrarily picked a equilateral triangle with side lengths 2, and then we dropped a bisector from this vertex. It bisects. We say it bisects. Okay, so each of these is 2. But based on geometry, because of the properties of the triangle, this bisector is perpendicular and it cuts this line in half. I didn't draw it. This isn't drawn to scale. Or this isn't drawn, I wish I could have drawn this better. And so with that, we could figure out we could use the Pythagorean theorem to solve for this height. And what we got is these are exact values. And so there you go. Now you can, for any 30, 60, 90 triangle, no matter what the side lengths, you could get the trig functions. We did a similar thing for a 45, 45, 90 triangle. However, we were able to do this because it worked out well. The fact that this bisector was perpendicular to the base and it cut the base in half. And what you can imagine, though, it doesn't work out so well for just any angle. If you want to find the trig functions of 21.1 degrees, you can't just do like a geometry analysis like this and get the exact answer. Okay, so what do? How do we get, if theta is 21.1 degrees, how do we get sine of theta? Well, the way we as engineers or people in business or just, people that are using just applied mathematics, the way we get this is we use our calculators. Okay, but that brings up the question then, well, how do the programmers, which I would assume the majority of these programmers are like math graduates with math degrees, things like that. What do these programmers do? Well, they use numerical methods to come up with approximations for the trig functions of something like this. Most angles, you can't get an exact value for the trig function. Like, here we know sine of 30 is 1/2. Or cosine of 30 is √3/2. That's an exact value. Most angles, you can't get an exact value. And so you can do a YouTube search and you can find some interesting videos where it's like programmers talking about how they would find accurate numerical approximations to different things in like things like calculators, for example. In particular, you can see how they do trig functions. Now, just to give you kind of a sense of how they might do this, they could do this with like the general definition, if you think about it. You just need to come up with a way to like numerically dial in this vector here being at the angle you want, let's say from the horizontal. So this is going to be 121 degrees. Let's say this is 121. Well, you have to get this 21 degrees from the horizontal, kind of dial that in, and then do like a numerical approximation on like of the coordinates of a point on the line. And then you just, to see the accuracy, you just kind of add the inaccuracy of dialing in the angle to the inaccuracy of the points. But with computers, it's really small, and then that's like a numerical approximation. But I'm sure what I just said was really unsophisticated. With people that do this professionally, have tricks and whatnot to really get extremely accurate values, but it's still approximations. Now, but another thing you can think about, though, we're going to learn in chapter 3 about the unit circle. And all the unit circle is like the general definition, but with radius equal to 1. And what we're going to see is when we use angles and represent angles in radians, that it ends up being like the sine. Like if you have a point on the unit circle, okay, this represents an angle, right? That represents this angle. Well, the sine and the cosine, and actually I don't think you even have to be in radians. The sine and the cosine are going to be the coordinates, right? Adjacent over hypotenuse, opposite over hypotenuse. That's just equal to the coordinates. And I think, and we'll talk about radians actually makes it even more simple to calculate the trig functions, but just using the unit circle can make it more efficient to like do a numerical approximation of the trig functions. And I think radians, it takes it even a step further. You can find the trig function values in radians of angle measure and then just kind of convert that back. But that's the idea. That's how we get trig functions of just any random angle. We use a calculator. We rely on math majors or professionals working in math to program these highly accurate numerical approximations of angles of trig functions into the calculator, and we retrieve the trig function approximation from the calculator. However, just note, it's not like you can't type what the sine of 30 is into the calculator. It'll give you the exact answer in that case anyway. Okay, so with that, if we take a look at section 2.3, there's really not much to this section. They talk about inputting angles into your calculator to get trig function values. So, I'm not going to tell you how to get a trig function value from your calculator. I think you're probably familiar with that. Here, trig, you just pick a trig function, and you can see I can choose between radian or degree mode. So cosine of 30 is 2, or that's cosecant 30. That's it. Tangent of, let's do 221. It will give you an exact value if it can. This means it couldn't give us an exact value. Well, this is the exact value, just tangent of 41. That's the exact value. It couldn't give us an actual more simplified exact value. Here, we're picking like a angle with, where the reference angle is 30, 60, or 45, and we'll get a value. But so what we do here, well, you see the approximate symbol, you do, and there you go. That's how you get an approximate value. And so this section talks about, getting approximate values with your calculator just like that. But what you do with that is that helps you to solve. So in the next section, we're just going to go through the process of, in the next section, we talk about solving right triangles. And what do they mean by solving right triangles? You just have any right triangle, and you've got just only certain information about it. Maybe you don't know any of the angles, but you know some of the sides. Maybe you know the angles, but you don't know all the sides, whatever, and you want to solve for everything. You want to get all the side lengths and all of the angles. That's solving a right triangle. So in this section, they do example problems where it's not about solving right triangles, but it's about solving real-life applications that involve right triangles, but it's not about here they're saying finding the grade. So I guess maybe you're solving for the angle, or you're solving for how much you have to go up. So something like that. It still requires you to solve a right triangle. You need to get either get this height or get this angle or something. And to solve problems like this, we can't do it with the methods that we learned before this section, where we were just evaluating trig functions given certain information, like given a point in a plane or whatever. Why not? Because if we already knew the point in the plane, or if we already knew the line that represents the angle, then we'd already have the problem solved, right? The problem's already solved in those cases. We would just those problems were just about learning about trig functions, in general, we need to be able to, we need to solve the problem. We don't have all the information, so we need to type into our calculator to get what the sine, the cosine, the tangent of some angle is, and then we can solve for the side lengths or whatever we're looking for. That's how you're really solving problems in trigonometry. Now, there are problems where, like I said, we might, maybe we have like some length information, side length information, but we need to find the angle. And so to do that, we'll need to like go in reverse. We'll have like the sine of something is equal, and we'll have this, and we need to like go in reverse. And so I've mentioned this already before. What that is we need to take the inverse of the trig functions. And so we're going to talk about inverses in detail in a later chapter, but the textbook points out here that, so to find the measure of an angle having a certain trig function value, calculators have three inverse functions: inverse sine, inverse cosine, inverse tangent. If x is an approximate number, then the inverse will give, and the calculator just gives the measure of the angle whose sine, cosine, or tangent is just that approximate value, which, that makes sense. And so they're talking about that's, so let's see. Yeah, there's the inverses, right? But like one thing to note though is that when you do an inverse, like let's say we do the inverse tangent of 1 here. And we're going to learn about this in detail in a later chapter. We get 45, not 225. So what's that about? Well, what happens is, in order to actually make inverses work, inverse trig functions, well, I'm calling it an inverse trig function, right? Well, functions don't have more than one output corresponding to the same input. So this, when you put in 1 into the inverse tangent, you can only return 45 or 225. You can't return both if it's going to be a function. So the outputs, the ranges of inverse trig functions are limited. But it's not that big of a deal when you see, like, for the applications you need to use the inverses, it's not that big of a deal that the ranges are limited. Okay, but if we did so inverse tangent of this, it gives 41 point, like, it didn't give the exact value, but if we did inverse tangent of this, it'll give the exact value. So that's the idea. Again, we're going to talk about in the next section solving right triangles. You have some information, angle or side information, you want to solve for the rest. If you need to find an angle, solve for an angle, then we're going to use the inverse trig functions in the calculator, in our calculators. But as far as the specifics on inverse trig functions, we're going to get into that later. We're going to learn those in detail. But if you already have the angle, then you just use regular trig functions to find the sides. And so that's solving for triangle. That's solving triangles. But in the example problems for this chapter, we're going to work actual examples that aren't about triangles, or right triangles, but they involve right triangles. It's like this, right? It's not about a right triangle, but the nature of the problem, it involves solving a right triangle to get some angle or height or whatever. Okay, so what else does it say in this section? That's pretty much it. We learn how to find exact function values for special angles and for angles having special reference angles earlier in this chapter. In this section, we investigate how calculators provide approximations for function values of angles that do not satisfy these conditions. Yeah, so we could solve for exact values of the special angles, 30, 60, 45, and then any other angle that has those angles as a reference angle. But again, it's the other ones, there's so many other ones that you just can't solve for exact values that way. So we use our calculators that are like behind the scenes. It's doing a really accurate numerical approximation of any angle we want. Here they just mentioned that you want to check the mode you're in, if you're in degree mode or radian mode. Also remember that if the angle or the reference angle is not a special or quadrantal angle, then the value given by the calculator is an approximation. And even if the angle or reference angle is a special angle, the value given by the calculator will often be an approximation. Yeah, it just depends on if it involves a special angle, but you input a decimal into it, it's still going to give you an approximation. So just, it's just good to know this kind of stuff. And so, yeah, it looks like the only angles that we can solve for exactly are just the special angles, 30, 60, and 45. So that's interesting. I would have thought that, mathematicians, like if you went to like some other more detailed math trigonometry books, that maybe there was other angles that they could solve for exactly, but it looks like that's not the case. Oh yeah, and then there's also quadrantal angles we can solve for exactly, right? A lot of those. Like we could get the sine of 0 is 0, the cosine of 90 is 0. So we also solve for those exactly as well. Okay, so here's just an example of like finding a trig function values with the calculator. To me, we're not going to work problems like this. I mean, yeah, you're just typing in secant of 97.977 into your calculator and making sure it's in degree mode. And we're going to work a bunch of examples like this. You know, there's like real life examples that involve right triangles, like solving for angles or sides of a right triangle to solve the problem, but they're not actually about right triangles. In the next section, we're just going to talk about, like, they talk about solving right triangles, which is like the same thing, but like one is like a real life application, the other is like pure geometry. So, okay, let's work some example problems.